So next we want to talk about what effect do higher order roots have. So higher order roots are when there is a multiplicity or order, or the degree on the root is greater than 1. So what does multiplicity, order, and degree mean? That is really just the exponent on the factor. So if we go back to our examples, so with our quartic functions here, when the degree was 2, or when it has a multiplicity of 2, or an order of 2, or some people say a double root, we want to see what happened to our actual graph. So the bracket that had a 2 on it, it was at x equals 3. So if we go down and we look at what happens at x equals 3, we'll see that it doesn't go straight through the x-intercept. It actually bounces off. So it causes that bounce. And if we look at other places where there are 2's, so for example here and here, both these roots have a multiplicity of 2. And if we look at both of the roots, once again, it doesn't go straight through the x-intercept like normal. It hits that x-intercept and it bounces off. It sort of forms a little parabolic shape, which makes sense because the degree is 2, and degree 2 things are parabolas. So it forms that U shape, that nice bounce, every time there is a 2 on the factor. So every time the factor has a multiplicity of 2. Okay. If we look at when there is a multiplicity of 3, so for example when x equals -1 here, when x equals -1, it doesn't bounce this time. It has that wave, that cubic shape when it passes through. And we actually officially call that a point of inflection. So when it was degree 2 on the factor, it caused a bounce like a parabola. And when it was degree 3 on the factor, it causes a wave like a cubic function does. And then when it's degree 4, just like degree 2, it causes a bounce. It's just a flatter bounce. And that's actually going to be true for all exponents on factors. If they're even, it's going to cause bounces, and if they're odd, it's going to cause waves. So let's write that out. So what effect do equal roots have? So that's when there's a power of 2 on it. It causes a bounce. And a more official way of saying that is a turning point. And you might also hear it referred to as being tangent to the x-axis, meaning it doesn't go through the x-axis, it just hits it once and then bounces right off. What effects do degree 3 roots have on the graph? So if there's a multiplicity of 3 or an order of 3, that causes a wave. And more officially, it's called a point of inflection. And if you go to study on calculus, you'll learn a lot more about points of inflection. So down here, I've just given you guys a couple more examples of those bounces and waves. Okay. Anytime when the root had degree 2, there's a bounce. If the root has degree 1, you just pass straight through the x-intercept like normal. Okay. And similarly over here, the root this time has degree 3, and you'll notice that we have that cubic wave going through the root. So let's work on some examples here. So for each of these, the easiest thing to start with is the degree. We're actually going to fill out sort of a mini table that I'm going to create here. And once we get all the information, it'll be much easier to graph. So we want the degree. We want the sign of the leading coefficient. We're going to want end behavior. And I'll shorten that to EB most of the time. We're going to want to state the x-intercepts, and we're going to want to state the y-intercept. And once we have all that information, we're going to pretty accurately be able to sketch this graph. I say pretty accurately because there is going to be a little bit of hand waving going on. But to properly sketch the graphs, we need calculus. So we're not quite there yet. So let's fill this out. So for the first one here, the degree. So if we look at this equation, there's 3 brackets. If we multiplied them out, it would have been x times x times x. So that is a degree 3 function. It is an odd degree. If we look at the sign of the leading coefficient, so if we imagined multiplying out those x's, we would have gotten a positive x cubed. So the sign of the leading coefficient is positive. Okay, and if it's an odd degree function with a positive leading coefficient, then the end behaviors are going to look like that. So we know we're going to start down here somewhere, and we know we're going to end up here somewhere. Okay, next, the x-intercepts. So we can read those off out of each bracket. It would be 4, 2, -3. And the y-intercept. Okay, so to find the y-intercept, we're just going to sub 0 in for x. In this case, -4 times -2 is 8, times 3 is 24. So let's start by sketching in our x-intercepts and our y-intercept. And we do need a nice scale here. And then for my y-intercept, I'm going to magically make this 24. Okay, so my x-intercepts were 4, 2, and -3. My y-intercept is 24. Okay, and there's no special shape on any of the intercepts. So every time we hit an intercept, we're just going to go straight through it like normal. Okay. We already know the end behavior goes from bottom to the top corner. Okay. So now we're just going to start drawing. So we're going to start at our bottom corner, because that's where the end behavior starts. And we're going to draw and pass through that intercept. At some point, we have to turn around. We have to cross through our y-intercept. It's sort of like a weird connect the dots. We're going to cross through our next x-intercept, turn around somewhere, it doesn't matter how high or low, cross through the next intercept to get to our end behavior. And there's our sketch. So the hand wavy bit here is we don't actually know how high or low the max and the mins are. For all we know, maybe it turned around exactly at 24. But that won't always be the case. So how high or low it goes isn't really important to us. What we care about here is if there's special shapes, we care about the x-intercepts, and we care about the end behaviors in the y-intercept. Okay, so let's do the next one. We're going to do the exact same information again. So we're going to get degree. We're going to look at the leading coefficient, the end behaviors, the x-intercepts, and the y-intercepts. So I'd pause the video and take a minute and try and fill out this table. So the degree here is 4. There's those 4 brackets. If we multiply them out, the leading coefficient would be positive. It's an even degree with a positive leading coefficient, so just like a parabola, it would start and end up. The x-intercepts would be x equals 4, 2, -1, and -3. And the y-intercept, if we plugged in 0, would be -4 times -2 times 1 times 3, which will be positive 24 this time. So take a minute, write out a scale, graph the x and y intercepts, and try and graph it with the proper end behavior. Okay, so here are all my x, y intercepts and my end behaviors. So I'm going to start at my top end behavior here. There's no special degrees on any of the intercepts, so I'm just going to go down, pass through, turn around at some point, okay, roughly in the middle, pass through the y-intercept, turn around at some point, turn around again, pass through the next x-intercept, and I end up with my proper end behavior. If you've done something wrong, like you've gotten a sign of the y-intercept wrong or whatever it might be, chances are you're not going to be able to properly go through all of the points. Okay, so there is a little bit of a check and balance. Chances are if it works out, you've probably done it correctly, or you've made maybe 2 mistakes and that's why they canceled each other out. So give the next one a try and then I will show you the solution. So we're going to start down here in the third quadrant, and we're just passing through our x-intercepts. I didn't do a very good job, but imagine that passes through those x-intercepts. And there we have our final graph. So here we'll do one last example. So this one, the degree, it has 3 brackets, but one of them is squared. So to get the leading term, we'd actually have to do x squared times x, so that's x to the 4, times this -1. So our leading term would have been negative x to the 4. So the degree would be 4, and the leading coefficient, because of that negative, is going to be negative. And if it's degree 4, so an even degree and negative, then that means the end behaviors are going to be in the same direction, both downwards. Okay. For our x-intercepts, same as before, we're going to read them off out of the brackets. So x equals -2, 1, and 4. And our y-intercept would be the negative times 2 squared times -1 times -4. So that would give us a y-intercept of -16. So we can plot those. We have the -16, we've got the -2, we have the 1, we have the 4, and we know we're going to start down in the bottom corner and end down in the fourth quadrant. Okay. This time there is something special, right? There is that squared, and so that squared is going to cause a bounce on the x-intercept of x equals -2. Okay. So when we're sketching this, we're going to sketch it like normal, except because we know we're going to bounce at this -2, we're going to approach it and we're going to create sort of that parabola bounce shape. And we're going to bounce off, and then we continue like normal. Passing through the y-intercept, we go straight through all the other x-intercepts, turning around somewhere, and we end with the proper end behavior. And because we know that there is this bounce at 2, it might help you before you start actually sketching the graph at 2 to draw in the little U shape so that you know where you're going to connect it to. That might just help you get that shape right. So that is how we sketch polynomial functions. There will be more examples in the next lesson.